So we're all familiar from algebra with the idea of increasing and decreasing based on linear equations, where you know that if the slope is positive, a line is rising from the right to the left. If the slope is negative, it's falling from right to left. And if the slope of the line is 0, well, that just means that it's flat. Y equals 0x plus b. Well, that's just a flat line. And so, and you know, with functions, like let's say this one, let's say this is f of x. Like our lectures from last week, you know that the function increases, decreases, increases, and at the peaks and the troughs, it's flat. And increasing means that the first derivative of the function is greater than 0. That is, it's positive. Increase has to do with positive. The first derivative is positive. And the function decreasing, that is, it's the slope of the tangent lines are all negative. It's falling or decreasing from left to right. I'm going to put a sad face there, just to kind of, that's the, to go with the minus sign. Decreasing is when the derivative is negative. So the negative sign, negative is bad, it's decreasing. And that's kind of like the way that I think about increasing and decreasing functions, right? It's rising, it's falling. That's kind of like good, bad, positive, negative, increase, decrease. That's all totally easy, you know that. But now a function isn't just the increasing and decreasing aspects. Note, the function I just drew, if you just wanted to think about its increasing and decreasingness, you could like draw the function this way. This isn't the same function. This is a zigzag line I drew that goes up and down and up about the same way that function did, right? Like, is it clear from this drawing that the function should be or maybe this function looks like this. Well, that's not a function. Hold on. Okay, I didn't do a really good job here of squishing that into the margin. I'm just saying, maybe it looks like this. Well, it's not exactly increasing there. Okay, there we go. There, that's a believable function. Look, this function is like curved upwards. This function is like humped downwards on that interval. That's different, even though they both are rising. This function is kind of like humped over like that, scooped over all the way down until it gets here. This one kind of like scoops under, kind of like up there. They're both scooped under here, but then this one stays scooped like that. But this one is scooped like that and it humps over the other way. And now it's going that way. Both of these have the same increasing and decreasing properties. Both of them have the same first and second derivatives. I mean, these are junky graphs, but if they were real functions with all of the points at the right places, both of these would be represented. Their derivatives would tell you this same piece of information. Do you buy that? Given that these were differentiable functions and not just junky graphs. Both of them have the same properties in terms of increase, decrease. So what's the difference? What's the difference between this function and that one? The difference is that this function curves a different way. The exact way that a graph curves up, over, scooped, that it like bends and wiggles, the shape of the graph, the shape beyond just up and down, the exact way that each function curves, bends, and wiggles. The technical term for that is concavity. concavity is the exact curvature of the function at a given point. And overall, over all of the points of it, it has a certain concavity everywhere that makes that line distinct to this one, the curve rather. Okay, well, I'm going to just really fast. Just like the first derivative gives you whether the function is rising or falling, the exact curvature of the function, surprisingly, is related to the second derivative. And the second derivative tells you along the curve, at every single point on the curve, exactly what the curvature, the concavity is. This is very impressive. Just like the first derivative, let's write it this way, d over dx gives increase, if it's positive, decrease, if it's negative, O, and it gives you peaks or troughs give you your maxes and mins in the case that it's 0. The second derivative, using that notation, gives concavity. And this is amazing. This is amazing. Because that the first derivative gives you something like slope is pretty intuitive. There's no comparable aspect of a line to concavity because lines are just straight. It's kind of a different concept. We don't really think about concavity in geometry and stuff as much. You might think about it if you're an artist. You don't necessarily think about the exact elegant way that the curve bends. And yet that is contained entirely. Every single thing about it is contained in the second derivative. And what does this tell you? Look, I'm just saying, increase, decrease, plus how it bends, that is the concavity. This is everything that you could possibly know about the graph, except for the zeros and things like that. So basically, the entire graph of a function, except for just the specific values of like when you plug in a value of x, you get back this value of y, but the picture of the graph of the function is entirely contained in the first and derivative and the second derivative of the function. These two simple to carry out things that you can do to the function will then give you, essentially in numbers, you can compute all of the different points along the curve, and you can compute what the general shape of the curve is. You're seeing homework problems like that right now. I can't go into the whole method for you. There's a few steps that you will go through to do this. And what I want to discuss is, so you have to find the first derivative and then plug in a value. If you take the first derivative of the function and plug in a value x equals a, then if this is a positive number, it's greater than 0. Of course, that means that at that point, the function is increasing at x equals a. If it's a negative value, it's decreasing at x equals a. And if you plug in a into the derivative, it'll tell you that it's a peak or trough. Peak or valley at x equals a max or a min. I'm just saying, you take the derivative, you plug it in, you just check the sign. You're not looking at the number. You're just saying, is it plus, minus, or 0? And that tells you if it's increasing, decreasing, or not. Right? We're not asking how steep it is, what the number is. In just the same way, taking the second derivative of the function, plugging in the point x equals a after you've done that, this gives the concavity at the point x equals a. That is the exact curvature of the line. Now, what do I mean by that? Let's just go ahead and talk about what concavity is. Concavity has a few pieces of vocab that goes with it, okay? If your curve is like this at a point, it's scooped like a cup or a bowl, this is called concave up. It's opening upwards. And it's really easy to remember concave up because of the theory of emojis. You can turn any curve at any point into a smiley face if it's concave up. Just draw two little eyes on the curve, and if it looks like a smiley face, if it's happy, then it's concave up. Concave up is happy. If the curve is humped like that, like a hill, and you draw eyeballs on it, and suddenly your heart's just breaking because it looks so sad, this is concave down. And it's easy to remember the up or the down because the graph looks either happy when it's up or sad when it's down. This is just the vocab. It can either be concave up, concave down, or it can just be flat at a place. I'm going to come to flat. Well, let me just make a little more room. Concave up is happy. Concave down, you draw eyes above the graph and it's sad. And if it's neither curved upwards or downwards, it's just a flat line, or it's like this. It is kind of like curved one way then the other. It's curved both ways. So this is called a point of inflection. Inflection means the curve changes, just in general. Like if your inflection of your voice changes, you go from saying this to this. The curvature, the direction changes. Well, the inflection of the curve changes. And that's kind of like, meh, meh. So is there a nice way that these pictures, up, happy, smiley face, down, sad, that these relate to the functions in the same and the derivatives? And yes, of course. This is really easy. On the derivative side, you take the second derivative of the function, you plug in a point A to see if on that point the function is concave up or concave down. But in general, if the function is greater than the second derivative is greater than 0, that is, the second derivative is positive, then the function is concave up at a point or on an interval. Concave up, up, happy, positive, plus. All of these things kind of like in language have similar connotations. And that all has to do with the second derivative. Similarly, if your second derivative of the function is less than 0, that is, it has a negative sign in front of it, well, that's concave down. Concave down is like sad. It's negative, minus. So if you see a plus sign in front of the derivative, either of the whole function or at a point, particularly at a point, or a minus sign, you know that it's concave up or down respectively. And if your second derivative is 0, that means that at the point x equals a, comma, y equals f of x is a, oh, I didn't leave room for this, is called a point of inflection. Here. Let me get rid of the word meh. Then x equals a, y equals f of a, right? That point on the curve is a point of inflection. Remember, inflection means that it's changing from one concavity to the other. So at the point x equals a, when you plug that in, that the y value of the original function at that point on the curve, that xy point, is a point of inflection. If, like this, that xy point would be a point of inflection if it changes from being concave down. See how the graph is sad right there? Oh, it's so sad. Oh, see how the graph is happy there? Hey, I'm so glad for you. See? But right in between, it's like it's flat right there. The second derivative is 0. That's what that looks like, that point. Cool. Now, as far as your intervals go, it's really easy to find because just like, remember that the points of increase, that if the function changes, a change from rising to falling, it has to pass through a flat part, right? Your roller coaster is going up, flat, down. So changes of direction or increase, decrease, like this, they pass through a point where the derivative is 0. These x values, remember, are called critical numbers or critical values. I'll write that way. Critical numbers. That's what the x value is called. Well, your function goes from being concave down, for instance, to concave up. See, sad, happy. It has to pass through a place where the second derivative equals 0. So these x values, they don't have a special name like critical numbers, but the x values that are the roots of the second derivative, these tell you the x values of the points of inflection. And you know that on either side of these. So what does this tell you? If you know what the 0 of the derivative is, you know to one side of that, it's going to be increasing and the other side is going to be decreasing or vice versa, right? If it's changing directions, that means that it was going one way and now it's going the other way. That's what you know. That's why you know that's a maximum or a minimum. It was going up and now it's down or vice versa. Similarly, and so you can find your intervals of increase, decrease. Your intervals of increase, decrease are the intervals in between the critical numbers. Your critical numbers tell you where the function changes rising or falling. And in between those, you can solve for those. And in between those, you know you're going to have the intervals where it's increasing or decreasing. There's no other changes of direction in between the critical numbers because those numbers tell you that the derivative was 0. And it's just the same with the second derivative. The intervals in between these x values, the roots of the second derivative, are going to be the intervals of concave up or down. And just like in the case of increase, decrease, if you solve the second derivative for 0 at a value of x, you know that it's changing concavity at that value of x. That's what that means. And so either it was concave down and now it's concave up, or it was concave up and now it's concave down. But in any event, these x values identify the places that the function is rising and then it changes to falling and vice versa. These x values, the roots of the second derivative, identify all of the places where the intervals of concave up and concave down are broken apart. So it's really easy to identify those intervals by taking the derivatives, solving for the roots, that is the zeros, the x values that make the derivatives equal 0. And then just, you know that for all of the intervals in between, those are going to be concave up and concave down. How do you know which one? Take any value of x inside one of those intervals, a really easy one to solve for, plug it in and see if it's a positive number or a negative number. That will tell you if it's concave up, concave down, increasing, decreasing, or whatever on that piece of the interval. Cool? And that is, I think, most of the stuff I have to say about concavity.